Welcome to the place where we gain knowledge through the lens of creativity. I am Aaron Dworkin, and this is Artful Science. Thanks again for joining me here on Artful Science. Today's show is Twinkle Twinkle Little Star, Adaptive Optics and How We See the Universe. And our guest is Céline Dojaville, who is Australian National University Translational Fellow and Advanced Instrumentation and the Technology Center's Deputy Director. Céline, welcome to the show.
Thank you very much. Thank you for having me.
So, I figured we would just delve right in, as I think about this work that you do, which is all centered around what's referred to as adaptive optics. What are adaptive optics? And, I used to have a telescope and loved, looking at the planets, being able to see, the rings of Saturn and being able to see, some detail on the moon and those types of things. So are adaptive optics just kind of a fancy word for telescope, or tell us a little more?
Yes, adaptive optics is a technology that is improving the performance of ground-based telescopes. The problem we have when we observe stars or anything else in space from the ground is that the light travels through Earth's atmosphere, and that atmosphere distorts the light. So you can't get really sharp images from the ground unless you use that technique called adaptive optics.
Gotcha. And so when we think about the adaptive optics, I think about, when I was, a kid and I used to walk through this cornfield going to the local movie theater. And I would always look up at the stars at night and, this idea of the twinkling stars. Do adaptive optics literally, if you will, kind of take the twinkle out of the stars? Is that literally what's happening?
Yes, that's the idea. The stars only twinkle because the light is going through our atmosphere. If you were looking at stars from space, like if you're on the International Space Station, the stars don't twinkle. So adaptive optics is here to remove that twinkle and sharpen images at the focus of our ground-based telescopes.
Gotcha. And so when we think about some of these extraordinary photos that we might see of other planets and even of galaxies, celestial objects, are we seeing that through adaptive optics?
So you can get pictures from space telescopes, and they're nice and sharp, but you can also get the same pictures from the ground using ground-based telescopes and adaptive optics. The only difference is usually you don't use the same wavelength, the same color. So for instance, from space, you typically want to be observing in the visible spectrum, so the light that our eyes can see, whereas from the ground with adaptive optics, it's easier to operate in the infrared, and adaptive optics works well in that region of the spectrum.
Gotcha. And so comparatively, looking at space-based telescopes versus adaptive optics, well, my first question is, are adaptive optics then not used on space-based telescopes at all? It's just not needed or relevant there? Would that be accurate?
Well, a similar technology can be used to improve the performance of space telescopes, but it uses the similar principles, but it's not quite the same, because on Earth you have to do adaptive optics really fast. What you do is you apply a correction to your optic about once every thousandths of a second, whereas in space there is no distortions that happen that fast. So maybe you need to make a correction, once every second or minute or something.
Gotcha. So just to delve into this a little more, with adaptive optics, if we take a normal telescope, if you will, or a traditional telescope, it's taking the light and refracting it ultimately right where we see it and ultimately in the lens. With adaptive optics, what's actually happening to the light? How are you adjusting, and how can you adjust that quickly to what's happening because of the atmosphere?
Yes, that's a very interesting question. So it delves into how you actually do adaptive optics in practice. The main component of an adaptive optics system is usually a deformable mirror. So instead of having a fixed surface, like on a regular telescope, what you want to do is bounce the light off a mirror whose shape you can change in real time. In order to change that shape and know how to change it, you first have to measure what the deformations are that are introduced by the atmosphere. And you do that with what's called a wavefront sensor. So that system, the wavefront sensor, makes the measurement. Then a computer calculates what shape to give the deformable mirror. You apply that shape, and by the time the light bounces off that deformable mirror, it corrects the deformations that were on the light front. And you do that really fast, as I said, about a kilohertz, in order to keep up with the changes in the atmosphere.
Wow, right? So, okay, so you partially just totally blew my mind with that. So also, as I continue to wrap my head around it, remember, coming from an artist's perspective, so how are you able to adjust the surface of a mirror in that amount of time? So I think about a mirror, how is it adjustable?
So you can think of it as a thin membrane at the surface of the mirror, and underneath you have what we call actuators, and they push and pull on the surface so that they change the shape. And there's different technologies to do that, but that's the general idea.
Got you. Great. And so, and probably just my last question around this part of it is that obviously it's adjusting based on those fluctuations in the atmosphere. How are you able to know or determine exactly what those are in the atmosphere?
Right. That's a good question. I haven't explained how you capture the light and make the measurement. What you need is a point source of light high in the atmosphere. So if you're, for instance, looking at a very bright star, a natural star, you use the light from that star to probe the atmosphere. Most often, of course, we're interested in looking at dim objects, and there's just not enough information coming from that object, not enough light. So we create our own star called an artificial star with a laser, and we also call that star a laser guide star. What we do is send a beam of light, a laser light, which is bright orange, that is able to excite sodium atoms that are located about 100 kilometers above the ground in the mesosphere. When these atoms are excited by that orange laser, they glow. And so they create that point source of light above the atmosphere. And now with our telescopes on the ground, we look at that light, at that artificial star, and that is the information we use to measure the deformations introduced by the atmosphere.
Wow. And then you apply the response to that thousands of times. Wow, that is, it really is truly extraordinary. So this incredible technology, which I understand, and now we're able to, if you will, really be able to see much more clearly, is that something, in other words, ultimately, say for an artist, for a general citizen, ultimately, how will we benefit from this ability to be able to see better our, the celestial heavens?
Well, there are many applications to that. One of the first application was to use it for astronomy and just improve the quality of the data, the images, and the spectrum we get of objects in space, stars, galaxies, and just improve the science and the astrophysics that goes behind it. There's also other applications that make use of adaptive optics, and we're slowly translating the technology into these areas like space situational awareness. So this domain looks at objects that are orbiting the Earth, and typically man-made objects. So we're talking about satellites that have been sent around the Earth at low Earth orbit or geostationary orbit. And we need to know where these objects are with high precision, because we want to avoid collisions between those objects and defunct satellites or space debris or space junk, we call them, that are still orbiting the Earth, even though they are not active satellites anymore. So we need to know where these are. And to do that with high precision from the ground, you also want to use adaptive optics to improve the performance of the ground-based sensors.
Gotcha. And is that becoming a problem more and more? And we even did a show on small satellites. Is space junk becoming more and more a problem where this technology is really needed to accurately map all of the things that are in orbit?
Yes, unfortunately, space debris is starting to be a major issue. There is a risk that because there is more and more objects sent to space, there's a higher probability of collisions. And when these collisions happen, they create more debris. And there could be a cascade effect, a snowballing effect, where you create so much debris that at some point there's a whole entire orbit that is cluttered with those debris. And you can't send active satellites there anymore because it wouldn't be possible to maintain them. So this is pollution in space, unfortunately, as we've already done on Earth. And as we're learning to use space, we have also to learn to do this in a sustainable and clean way.
Yeah, it's astounding that somehow what we already clearly know we did wrong here on Earth, we're already doing in this new frontier. So as you project forward with this extraordinary technology, is there a future that you see, say, 10 or 20 years down the road relating to adaptive optics? Do you think they'll go even further and enable us to do things we can't do today?
Yes, I think adaptive optics is going to be key in astronomy to answering those questions about exoplanets and looking at whether there is signs of life on other planets. So that's for astronomy. That's a really big deal, I think, for humanity. In the area of space situational awareness and looking at satellites, I would predict that adaptive optics is going to become mainstream eventually, and then be fitted on ground-based telescopes that are looking at those man-made satellites and making sure that they don't collide with other objects. And there's another application that we're starting to develop for adaptive optics, and it's used for space activities. It's laser communications between space and the ground, or ground and space. Again, here we're talking about using lasers to carry information, and this will significantly increase the amount of data that can be transmitted as opposed to the radio waves that we're using nowadays. And in order to improve, again, the performance of these laser communication links, adaptive optics will have a role to play.
Wow. So, well, and that sounds like another show for Artful Science, lasers and the information they can carry. So unfortunately, we're just about out of time, but I always need to ask of our guests, since we're here at this kind of intersection of the arts and sciences, do you have any artistic practice that you do and or artistic discipline that you love to observe and appreciate?
Yes, I have a few, actually. I used to be a dancer when I was younger, and I really enjoyed, dancing. I had to discontinue that activity because I had a knee injury. But a few years ago, I discovered the pleasure of singing in a choir, which is an activity I do on a regular basis now. And we perform, in front of general audiences. And it's just a wonderful way to connect with other people, other human beings, and create a very strong bond.
Oh, absolutely. Well, it's so wonderful that you're engaging in that way. And of course, in these ways with so many people, the impact you're having is tremendous. Céline Dojaville, thank you for helping us gain knowledge through the lens of creativity here on Artful Science.
You're very welcome. My pleasure.